Hey everybody, I'm going to cover topic 3.7 with you, which is about solutions and mixtures. A lot of the concepts in this section are a review from Regents Chemistry. We're going to talk about the components of solutions, how they're made, and how to perform molarity and dilution calculations. So for this, we're going to be able to calculate the number of solute particles, volume, or molarity. The molarity calculation is on your reference sheet. We're going to just review some vocabulary first. So as a review, solutions are homogeneous mixtures of two or more pure substances within the same phase. They could be solids, liquids, or gases. When you have a solution, this is the definition of homogeneous, the solute is dispersed uniformly throughout the solvent. When you're dealing with heterogeneous mixtures, as a contrast, these are not solutions, the macroscopic property, so the appearance of the mixture, depends on the particle's location in the mixture. But for solutions, the macroscopic properties do not vary throughout the sample. It appears uniform in composition. So any particular sample I would take would look extremely identical. So if you think Kool-Aid, if I take like a sip of Kool-Aid, every sip should taste the same. But if I had a salad, every forkful of my salad could have different properties because it's heterogeneous. The two parts of a solution are the solvent, which is the substance that has the greater quantity, and the solute is what you're putting into it in a lesser quantity. Also remember the words dilute versus concentrated. If I have a solution that is diluted, I'm not going to have as much solute in it as a solution that is more concentrated. These are just different types of solutions. It gives you solutes, the solvents. Air is a solution, right? A mixture of gases. Normally in here, you're going to be dealing with solid solutes dissolved in liquid solvents, but you could dissolve liquids in liquids like rubbing alcohol, hydrogen peroxide. Those are volume-based solutions based on liquids. Let me see what else in here. Alloys would be a solid solution, right? A uniform mixture of metals. When these things interact, and we'll talk about this in a little more detail, it's because of similar intermolecular forces, and we always say things are like dissolves like. When a solution forms, this is very important. You have to understand the mechanism of how it forms. The intermolecular forces between the solute and the solvent particles must be strong enough to compete with those between the solute particles only and between the solvent particles only. So there's kind of a competition of forces of attraction here. The solute that you're putting in, those particles are attracted to one another through some sort of force, right? Either dispersion force or dipole or hydrogen bonding. The solvent particles are also attracted to one another through intermolecular forces of some kind. So we need to break those forces between the solvent and solute and get them to interact with one another. When I have an ion, an ionic solid, and it dissolves, those ions will dissociate and separate and be surrounded by water molecules. A quick review of excuse me, I can't edit that. A quick review of types of solutions. You could have saturated, unsaturated, supersaturated. So if you have a saturated solution, you've like maxed out the capacity by which the solvent can hold solute particles. And if you add any more, it'll just settle to the bottom. It's at dynamic equilibrium. So the rate of dissolving equals the rate of crystallization. So if I have stuff settled at the bottom and I stir it up, some of the stuff at the bottom might dissolve as long as some of the stuff that was in the solution falls to the bottom. It's like an exchange. An unsaturated solution, the solute hasn't yet reached its maximum solubility, so I can still keep stirring more stuff in and it will completely dissolve at that temperature. And a supersaturated solution, it's kind of, the solvent is holding more than it normally could at that temperature, and it's unstable. So if I add just one more crystal to that supersaturated solution, what will happen is it will start to precipitate out and the whole thing will start to crystallize. There are different factors that affect solubility. Polarity of the molecules is one thing, right? So polar tends to dissolve in polar, nonpolar in nonpolar. The more similar the intermolecular forces between the solute and the solvent, the more likely they are to dissolve in one another. So you can see here why like cyclohexane wouldn't necessarily dissolve, but glucose would because of its polarity. Gases will become more soluble as their masses increase, because the larger molecules have the more highly polarizable electron cloud and will become more soluble, have stronger LDF to be able to interact with the water molecules. Also, pressure changes. So liquids and solids don't change much in terms of their solubility when you change the pressure, but gases will. Gases are more soluble under higher pressure, because under higher pressure, you're keeping them in one spot and kind of forcing those molecules to interact with the solvent. So if you think like a carbonated beverage, a pop, a pop. The CO2 stays dissolved in the water and makes carbonated water, right? Because it's under a lot of pressure. But as soon as you open it and release the pressure, the gas starts to move around and escape, and it bubbles out and is not soluble anymore. And eventually it will go flat. For temperature, in general, solids tend to get more soluble as you heat them up. And this was a solubility curve reference table that you had in Regents chemistry, similar to what's on the screen now. But gases will always become less soluble as you heat them up. Think about kinetic molecular theory. As I increase the temperature and the average kinetic energy of gas particles, they tend to spread out. They're moving faster. They're harder to contain. You're breaking those intermolecular forces more readily, and it will escape. So that warm soda is going to go flat as well. Now we're going to talk about calculations. The molarity calculation is on your reference sheet. This is a snip from the reference sheet. So you have the calculation that gives you like how many moles. You could also just use factor labeling. That's always my go-to. And then the molarity calculation is here. Capital M is molarity. It's moles of solute per liter of solution. You must use those units when you do molarity. So here is an example question. Oh, that should be a subscript, sorry. Calculate the molarity of a solution formed by dissolving 202 grams of potassium nitrate. This is the molar mass in 250 milliliters of water. So since we have the given mass and the gram formula mass, we can convert that to moles. We also could have done this via factor labeling, which is the same calculation, right? You're dividing and you get 2 moles. So here's the moles part. We have 250 milliliters. You must convert that to liters in order to get your molarity. You use the reference sheet, okay? Don't rely on your memory when they give you the calculations for these. Here's another example. What's the molarity of iodide ions in a solution that contains 56 grams of strontium iodide? Oh, I think this calculation is wrong, actually. In 1.65 liters of, oh no, that is right, sorry. Okay, so we have a mass and we have a volume, but it's asking us for the molarity of iodide ions, not the molarity of the compound. So there's gonna be one more step that we have to take. So first we can convert grams to moles. So 56 grams times 1 mole over 341.42 grams. That's the gram formula mass of strontium iodide. Now that's strontium, moles of strontium iodide. We want moles of iodide ions. All you got to do here is count how many iodines are in my compound. There's 2 moles of iodide ions in every 1 mole of strontium iodide. So once we do that step of 56 divided by 341.42 times 2, that gives us 0.328 moles of iodide ions divided by 1.65 liters, and that gives us 0.199 molar, which is the answer that I have here. The other way you could have done this is just gotten the molarity of the strontium iodide and then doubled it, because there's twice as many iodines for every 1 unit of strontium iodide. So be careful with questions like this. If they're asking you for the concentration of one of the ions, count how many of the ions are in that solution. Because every time I have strontium iodide go into water and separate, 1 unit of SrI2 dissociates into 1 strontium and 2 iodines. So there's twice as many iodines present. This question is similar. How many moles of sodium ions are in 245 milliliters of 0.1 molar sodium phosphate? So same deal here. We're given the molarity, we're given the volume. So I'm going to use factor labeling right off the bat. 0.245 liters times 0.1 mole per liter, or 0.100 moles per liter. That's of sodium phosphate. I need to know how many sodium ions are in it. So there's 3 moles of sodium ions for every 1 mole of sodium phosphate. And that gives me the answer of 0.0735 moles of sodium ions. If it just asked me for how many moles of sodium phosphate, I wouldn't do that last step, right? I would stop there. You do need to know experimentally how a solution is made, and this kind of stinks that we can't do this together, but this is a procedure you need to know. If you're dealing with a solid solute, you would need an electronic balance, obviously, to weigh out the appropriate amount. And then you would also need what's called a volumetric flask. So this is a volumetric flask. It doesn't have any markings on the bottom part. It just has like 1 mark on the neck that tells you so this is a 1 liter volumetric flask. So this would be pretty hefty in size. And it just has 1 mark on it. And if you fill your solution and you hit your meniscus at that mark, that's exactly 1 liter. So there's no other marks on it. It's only meant to measure 1 particular volume, which seems kind of silly, but it's super precise. We have these in all different sizes in the lab. We have 10s, 25s, 50s, 100s, 250s, 500s, and 1 liters. So what you would do is you would do all the background calculations first, if you know what molarity you want, and then you would measure out the mass of your solute. You would dissolve it in a little bit of water, and then you would keep filling up to that meniscus mark, and then you would invert to thoroughly mix. So a volumetric flask and a balance, a funnel, something like that. So this question, how do you make a 250 milliliter solution of 0.1 molar sodium hydroxide? This is actually something that you would have to do in a lab. So we need the gram formula mass of sodium hydroxide, which is 40 grams per mole. So we can figure out how many grams of sodium hydroxide we need in this solution. So 0.25 liters times 0.1 moles per liter times 40 grams per mole gives us 1 gram. We need 1.00 grams of sodium hydroxide. So what would I do? I would measure out 1 gram of sodium hydroxide exactly. I would pour it, this is beautiful. I would pour it in that powder into the bottom of my volumetric flask. I would add distilled water, just a little bit to get it, swirl it around to dissolve it. And then I would make sure my flask is a 250 milliliter flask. And then I would continue to fill with DI water up to that mark. A dilution is another calculation you need to be able to do. Dilution is made to reduce the concentration of a solute by adding solvent to it. This is the shorthand way of doing it. M1, this is not on your reference sheet, but it's easy enough to remember. M1V1 equals M2V2. So your original molarity and volume equals your new molarity and volume, because the reason you're not changing moles of solute. So your moles of solute will be equal, you're just adding solvent to it. So if my stock solution of yellow dye is 5 times 10 to the negative 5th molar, and I dilute it by adding 15 mils of water, what is the molarity of the dilution? So I have my original molarity, which is 5 times 10 to the negative 5th. My original volume is 5 milliliters. It doesn't matter what volume unit I use because I'm using milliliters on both sides. It doesn't matter. I'm trying to figure out the new molarity. Now, what's the new volume of my solution? It says I have a 5 milliliter stock solution and I add 15 milliliters of water. So the new volume of my solution is 20 milliliters, not 15, right? It's 20 because I dumped 15 more in. So when you do that calculation, your final molarity is 1.25 times 10 to the negative 5th molar. So I've diluted it, so this concentration is less than the original. Oh, and that is the end. So that's a quick review of what makes a solution, how to calculate molarity of a solution, calculate molarity of ions, how to make a solution, and how to do dilution. Stay tuned.